All right, yeah. Let's start by talking about homeworky things. So somebody asks about indirect proofs. Yes, you're supposed to negate the conclusion and then argue to a contradiction. Um, so typically, we're trying to prove if X, then Y. So direct proof, we start off with X and we do some other things and we end up proving Y. An indirect proof, we start off with X and we start off with not Y, and we argue and eventually we come up with false, and therefore we conclude Y is true. And my only warning on indirect proofs was make sure that you're not just doing a direct proof. So don't do this. Don't do X, not Y, and then do a bunch of stuff and then prove Y using a direct proof, and then say, you know, we've got Y and not Y, which is false, therefore Y. Because this is really just your direct proof with some fancy language before and after, right? The contradiction that you're trying to reach here is not the contradiction that you get by proving Y and then saying, so Y can't be false. It's usually something different, right? We actually use this in a direct proof of, you know, something contradictory. And when you get it, you know it, right? It's really obvious that there's a contradiction there. So let's run through an example of an indirect proof. Let me go to the problem set here. So let's see. I'm giving you odd problems. So let's pick on 3C. That looks, yeah, let's pick on 3D. Let's not do the double implication. So P implies Q, Q implies R, not P and R, P or R. I'm gonna get myself in trouble because I haven't done this ahead of time. P implies Q, Q implies R, not P and R, P or R, therefore R. When you copy problems like that, don't accidentally copy like the first part of one problem and the second part of a different problem, because you'll end up with something really weird. I had a friend who tried making zucchini bread, and halfway through the recipe, something flipped the page in his book, and he finished the recipe with a recipe for something totally different, and got something strange. All right, let's do an indirect proof. So we're going to assume not R. So that's a negation of the hypothesis. And we want to argue to a contradiction. Well, I mean, P implies Q, Q implies R. Those kind of look like we should slap them together and get a chain rule, right? So P implies Q. And I'm going to be a little quick and dirty. So this is a chain rule of 2 and 3, so we know that P implies R. But we have not R, and so we can use indirect reasoning and conclude not P. Because not R and the fact that if P is true, R must be true tells us that P is not true. And then this rule right here says P or R. That's a hypothesis. Well, since we know P or R is true and P is not true, that tells us R must be true. And that's, I don't know what that is, that's some rule. And that's a contradiction. All right. Got a question about section 3.4 number 2. Let me see what that looks like. 3.4 number 2. Show that the common fallacy, if P then Q and not P implies not Q. Show that it's not a law of logic. Yeah, I think that was disjunctive simplification. Do I state my counterexample by stating a simple proposition using P and Q and show that it is false due to contradicting props, or am I supposed to do a proof that argues to a contradiction? You're doing a demonstration here. So you can say, you know, let P be the proposition such and such, let Q be the proposition such and such, and then, you know, state that this is true, and hopefully you've picked propositions where it's clear that if P then Q, and, you know, state that this is also true, but state that this is false. And so the goal here is to pick propositions where, you know, clearly this and this are true, but this is definitely false. So that's just an example. All right, I want to take another pass by the truth table for implications for this if P then Q business, because this is a little odd, and I think the difficulties in working with this lead people to run far away from implications. And so when doing proofs, a lot of people, as soon as they see a if P then Q, they use conditional equivalence and they change it into you know, P or Q or not P. And you can do that, there's nothing wrong with it, but for example, you know, P implies Q, Q implies R, that should get you really quickly to P implies R. If you've jumped over to the world of conditional equivalence, this is Q or not P, this is R or not Q, and now you've got to do Q or not P, ended with R or not Q, and you can distribute and all that kind of stuff, and eventually you'll end up with this, right? But the chain rule would get you there so much quicker. So let's embrace our conditional friends, and let's look at the truth table. And I'm going to pick on this pair of propositions I used when I first talked about this. Suppose P is a proposition that some number n is bigger than 10. And Q is the proposition that n is bigger than 5. For any value of n you pick, if P then Q. Any integer you pick, if it's bigger than 10, it's definitely bigger than 5. So let's pick some n's and fill in this truth table by using some specific values. So I'm going to pick a value n equals 100. Well, n is bigger than 10, so in this case P is true. N is bigger than 5, so in this case Q is true. And we know that, you know, if n is bigger than 10, it's bigger than 5, so this is definitely going to be true. Right? This is This is always true for any n, right? Forget about this. Any integer you pick, if it's bigger than 10, it's bigger than 5. Agreed? So for any n I pick, if p then q should be true. So let's try some representative n's. If n is 100, right, that's true, that's true. This should be true. If n is equal to 0, well, it's not bigger than 10, so p is false. It's not bigger than 5, so q is false. But we know that for any n, p implies q should be true. So I still got to put a true in that row of the truth table. Let's try n equals 7. So is n bigger than 10? No, so p is false. Is n bigger than 5? Yes, so q is true. And we know that for any n, including n equals 7, if p then q should be true. So we've got 3 rows of our truth table filled out. What about this one? Well, this is clearly false. If there was a value of n for which p was true and q was false, then this implication is automatically false, because this says if p is true, q is true. So if I had an n where p was true and q was false, this is certainly going to be false. But guess what? There's no such n where p is true and q is false. So this is one way to derive the truth table for implication. Now you kind of have to believe that since it worked in this case, we're going to get the same truth table no matter what p and q are. But this is the way in which we can see this if false then anything, right? If we have something false implying something true, then the implication is true. But if we have something false implying something false, the implication is still true. And it doesn't make sense in a common sense kind of way, but logically it's valid. And the fact that, you know, for these particular propositions I don't find any n in here, that's a reflection of the fact that this implication statement is false. So I don't know if that helps or hurts or is neutral, but that's the way these truth tables work out. And so if you have a truth table involving, you know, if p then q, put in a column for this, right? But if it's some more complex expression, if you wanted to do, you know, s and t implies u or v, right? Make a column for s and t, make a column for u or v, and anywhere that first column is true and the second column is false, the implication is false. Anywhere else it's true. All right, other questions? What about if the left side of the implication sign is always false, but the right side is true half the time? If the left side's false, the implication is true. Doesn't matter if q is true or false. So let p be the proposition 1 plus 1 equals 3. Let q be the proposition the sun is a giant light bulb. Painted on the roof of a big dome. So the Star Trek thing where you climb the mountains and touch the sky. This is a true statement. If 1 plus 1 equals 3, then the sun is a giant light bulb painted on the roof of a big dome. That is a true proposition. Which seems weird, of course. If Q implies P, so Q implies P is something very different, but since I picked something that was absurd here, right, in this case, this is also true. But let's use the same proposition P and let R be the proposition, my name is Nick. Well, P implies R, this is true. If 1 plus 1 equals 3, then my name is Nick. But R implies P is false. If my name is Nick, then 1 plus 1 equals 3. Well, that is not a true proposition. Because that's true, that's false. True, false, the implication is false. So this takes getting used to, but you know, the more you work on these problems, the more you kind of think about it, and the more you get confused by it, the more you'll understand it. All right, cool. Other questions? All right, let's talk about number theory. You ever notice people always talk about like introduction to such and such, introduction to programming, introduction to calculus? It's like, if you're going to learn something, don't tell people it's just an introduction. Let's talk about number theory, a bit of number theory. So number theory is one of these topics that is easily accessible. Number theory mostly deals with integers, positive integers, whole numbers, usually numbers bigger than 1. And a lot of what we're going to do in number theory deals with dividing whole numbers. Right? We're not even going to worry about fractions. We're going to just take, 7 and divide it by 2, and what do we get? Well, we get mostly 3, but a little bit left over. That's number theory. And it's an area that we can write definitions for a lot of things, and the definitions involve, whole numbers and multiplication and division, and not a whole lot else. It's a subject that, in some ways is accessible to an elementary school level of mathematics. But it's an area that has some amazingly difficult problems, many of which are unsolved today. And it's an area in which the pursuit of answers to those problems has led to, the development of huge branches of mathematics that are complex and deep and beautiful. So it's an area that a lot of so-called amateur mathematicians take an interest in. It was my first love affair with math, was looking at number theory, and prime numbers in particular. And I think that's the case for a lot of people who get drawn into these kinds of things. So we're going to develop systematically some fundamental concepts in number theory, and I'm going to invite you to try to stay tuned in, even though the things we're talking about will generally seem like things that you already understand completely. For example, this question of when does one number divide another number? Well, that's simple, you know. 5 divides 25. 5 does not divide 26. But that right there is enough to get us into a world of complexity. So I'm going to give you a bunch of definitions, and we're gonna develop some of these foundational concepts. And like I say, I'll ask you to try to believe that this will get somewhere less obvious as we go. So let's start with divisibility. And we're going to stick with integers, so I'm not going to keep saying an integer or something from the set of integers, assume this is an integer. We'll just you know, we'll do integers from here on out. A divides B if there exists a C. I will say integer here because that's really important. If there exists an integer C such that B equals A times C. Okay, that's our fundamental definition. A divides B if B can be written as A times some integer. In this case, we also say A is a factor of B. We can say B is a multiple of A. Alright, so let me give you some notation. This is confusing but really important. If you miss this, you're going to be way off on all the homework and questions and everything that we talk about for the next few classes. So this is a really important piece of notation. If A divides B, we write A vertical pipe and B. So when you see this symbol in the book, in notes, whatever, that means A divides B. B is a multiple of A. A is a factor of B. This is a proposition. It's not an arithmetic operation. It's definitely not saying take A and divide it by B. It's not saying take B and divide it by A. It's not saying what's the remainder when B is divided by A. It's a proposition. It's the proposition that there exists an integer C such that B is equal to A times C. Alright, that's super important. So this symbol A vertical bar B is a proposition that B is a multiple of A. Alright, everybody good with that? 11 of us are good with that. The other 17 hopefully will catch that in the video. I could say really, really important a few more times. So for example, this is a true proposition. 3 divides 12. Why? Because 12 is 3 times 4. How about this? Is this true or false? It's true. Negative numbers are no different from positive numbers. In this case, 12 is negative 3 times the integer negative 4. How about this? 2 divides 0. And we gotta be careful, this isn't like 210. That's a vertical bar. 2 divides 0, true or false? Anyone else? Yeah, this is true. So this is true because 12 equals 4 times 3. This is true because 12 equals negative 4 times negative 3. This is true because 0 equals 0 times 2. In fact, anything other than 0 divides 0. Alright, what about 3 divides 7? True or false? Definitely false. Let's see, clarification. If we say A divides B, would that be the same as B divided by A? No. This is a proposition. 12 divided by 3 is not a proposition. It's not a declarative statement with a truth value. 3 divides 12 is a declarative statement. Or 12 is a multiple of 3, or 3 is a factor of 12. Those are propositions. So yeah, it's definitely different. Alright, so this is false. If we write this vertical bar with a slash through it, that's the negation of this proposition. So if we write A does not divide B, this is the proposition. A does not divide B. It's the negation of that proposition. So 3 does not divide 7. That's true. My 7 grew when I wrote my bar. Alright, got the idea? And there's really nothing trickier than this going on here. It's you know, this is a proposition that that's some integer multiple of that. That goes into that a whole number of times. But we can start doing some fun things with just that kind of humble beginning. So let's make a small theorem. Again, nothing but integers in sight. If A divides B and A divides C, then A divides B plus C. Yeah, weirdness-based fuzziness is okay. That's kind of what we're paying for here. Okay, theorem. If A divides B and A divides C, then A divides B plus C. Well, is it true? 3 divides 12, 3 divides 21. According to our theorem, 3 should divide 12 plus 21, which is 33. Hey, it does. So if you play around with this for different values of A, B, and C, you'll find that, you know, anything that's a multiple of A added to anything else that's a multiple of A still ends up being a multiple of A. This works out as a valid theorem when we throw examples at it. How the heck are we going to prove it? Anyone want to take a shot at a starting step? And it doesn't have to be a productive step, but what would be a possible first step for a proof of this theorem? State the hypothesis. A divides B. That's a hypothesis. If I'm getting paid by the line, I'm going to go ahead and state the second hypothesis. A divides C. That's a hypothesis also. Alright. What could we possibly do from here? And in the end, there's really only one thing we can do. Other than, you know, write poetry or something. We could negate the conclusion if we wanted to do an indirect proof. That will actually end up being a pretty hard way to do this. Let's see, state A divides B plus C as a hypothesis. That we definitely do not want to do, though. If we write this down as a hypothesis, anything else that we prove is only true if this is true. And remember, our goal is to prove this. So if we make that a hypothesis, then we've proven if this is true, this is true. So we're not going to write that down as a hypothesis. We're going to have to do something different. And then hope that we can eventually get to here. So this is hard. We don't have a lot to work with yet. We've only got 2 things written down. And we've used, you know, all the stuff we were given. A divides B, A divides C. But there still is one thing we can do. Develop an example of conclusion. We could do that. But we need something more than an example. So what did we do with even odd proofs? What did we do after we stated the hypotheses? Do you remember? So B plus C is not a proposition, unfortunately. GER would be good. That should be a valid step, or at least a reason for something. What did we do with even odds? What was the third step of our even odd proofs? Definition of divisibility. There we go. Right? We've written this funny symbol here. Let's say what that means. So what does it mean when we say A divides B? Well, A divides B if there exists an integer C such that B equals A times C. Well, I can't use C because I'm using C up here, but, you know, I could just as well say A divides B if there exists an integer K such that b equals a times k. That's the same definition. So let's go ahead and write that. So a divides b, this means there exists an integer k such that b equals a times k. That's the definition of divisibility. Alright, so you probably got an idea for the fourth step. Do the same thing. We know that a divides c, so there exists some integer such that c equals a times that integer. But I can't use k again. I'm going to have to pick a different integer. So I'm going to say there exists a j such that c equals a times j. That's the definition of divisibility. And you understand why I can't put k here. If I say c equals a times k, and I said b equals a times k, now I'm stating that b and c are equal to each other. And I don't know that. That's not a fact. There's nothing in here that says b and c are the same number. So if I write down that c equals a times k, I've written something that's probably not true. But there does exist some j, which is an integer such that c equals a times j. So let me go to my ignore section. And remember, putting the ignore up there and marking that off stops me from looking at this and taking off points because of what you write here. You can write anything you want here. You can call me names, you can write 1 plus 1 equals 3, right? And that's not part of your proof because you said ignore. But this is where you're thinking out loud. But it can help me to see where you're thinking out loud. If your proof isn't quite right, I can, follow your thinking better. So it's nice to put it on here. Okay, where am I trying to get to? I want to show that a divides b plus c, which means I want to show there exists some x such that b plus c equals a times x. That's helping me visualize what my goal is. If I can get to this point, if I could show that there's some x such that b plus c equals a times x, then I can say, therefore, by definition, a divides b plus c. So any ideas from what we've done so far how I can show that b plus c is equal to a times some integer? So we could define x as any integer. And then what? So I could say let x be an element of z. So we're trying to get to showing something about b plus c, and we just did some writing and we came up with formulas for b and c, and those formulas involve a, and we're hoping to write something as b plus c involving a. So yeah, let's substitute in. Let's just write down, for no particular reason, b plus c equals a times k plus a times j. And that's just, substitution 3 and 4. Now, there's no necessarily good reason why we wrote that. But no one can look at this and say, that's not true. You know, it is true. We know that B is AK, we know that C is AJ, so we know B plus C is AK plus AJ. Someone could look at it and say, that doesn't belong in your proof, there's no reason for that, and they might be right. But you know, like I say, you can write poetry in here if it's phrased as a proposition that is clearly true. You can put anything in here. I could say, you know, square root of 2 is not a member of Q. Does not do anything harmful to my proof. It might not help me, but as long as everything I'm writing is a true proposition, it's allowed to be part of my proof. And so, you know, I can write down B plus C equals A times K plus A times J. That's totally fine. But in fact, that is going to help us with our proof. So what can we do now? Keeping in mind what our goal is. Take out A. Perfect. So I will factor out the A and I'll write B plus C as A times K plus J. And that's algebra. And we wanted to show B plus C was A times some integer. And so now I'm just going to make the statement K plus J is an integer. Now how do we know that? Well, we know from statement 3 that K is an integer, and we know from statement 4 that J is an integer, and I'm just going to say properties of integers. So what kinds of properties of integers can we use? Well, the fact that adding, subtracting, multiplying integers always gives you an integer. Those are safe to use. Don't try to write a proof where you just say, you know, step 1, step 2, step 3, A divides B plus C, that's properties of integers. You got to do more work than that. But adding 2 integers gives you an integer, you can take that as a given. So now we've written B plus C is equal to A times some integer. Right, and that follows from 6, 7, and the definition of divisibility. Because that's what it means to say A divides B plus C. It means B plus C is equal to A times some integer, and that's what we've just shown. And so that's the end of our proof. So the first question to be asking is, do the steps of this proof make sense? Right? Do we understand how we go from here to here to here? Do we understand why each of these things is true, given the truth of the things above it? The second question to be asking is, given that each of these statements is true, did we in fact prove the thing we were trying to prove? And that's pretty unarguable. But then the third thing to be asking is, you know, how the heck do you do this? When you get a different question that looks nothing like this, how do we, you know, do the same kind of thing on a different question? That's what homework is, right? That's something you just figure out from doing this. And so the more problems you do, the more your brain starts to wire up circuits that will let you look at a totally different problem you've never seen before and still, you know, come up with you know, at least a good piece of a formal proof. And even though, you know, a proof is a search in an infinite search space, right? You're searching all the possible things that you could write down and trying to find the collection of things that leads you to your proof. In reality, most of these proofs end up looking more or less the same. So let me just show you another one. If A divides B and A divides C, then A divides B minus C. What's going to be exactly the same thing, right? We're going to say B minus C is equal to this, B minus C is equal to that, therefore A divides B minus C. So that's going to be really easy based on this. Let me show you a slightly different one. If A divides B and B divides C, then A divides C. Well, is it true? So 3 divides 15, 15 divides 150. Therefore 3 should divide 150. Hey, it does. 7 divides 21, and 21 divides 63. Therefore 7 should divide 63. Hey, it does. And if you play with a few examples a little deeper, right? How many times does 3 go into 15? 5 times. How many times does 15 go into 150? 10 times. How many times does 3 go into 150? 50 times. 5, 10, 50. 7 goes into 21 3 times. 21 into 63 3 times. 7 goes into 63 9 times. 3, 3, 9. Seeing patterns here. Yeah, indeed. So these patterns are a hint to how we might prove some of these things. So 1, A divides B, that's a hypothesis. 2, B divides C, that's a hypothesis. And you can write all your hypotheses in the beginning, or you can write them down as you need them. Sometimes there's red herrings in here that you won't actually use, but I'm just going to write down my hypotheses first, and then I'm going to use the definition of divisibility. So there exists an X such that B equals A times X. That's the definition of divisibility applied to statement 1. There exists a Y such that C equals B times Y. That's the definition of divisibility applied to statement 2. If you swap these around, you're going to end up, grabbing at straws to try to prove something that's probably not true. So be really careful with going from here to here. Do a double check, make sure it makes sense. So 3 divides 15, 15 equals 3 times something, yeah, that works. A divides B, 2 divides 100, so 100 equals 2 times something, yeah, that works. Okay, so we're still safe. Here's my ignore section. You can draw pictures or whatever. We're trying to show A divides C. We want C to be equal to A times something. Well, I've got C equal to B times something, but I've also got B equal to A times something. Substitution. A lot of substitution in these. C equals A times X times Y. And that's just propositions 4 and 3. And now we're done. Right, this is that step. Every proof has a step where there's like a little spark of inspiration. It's a bridge from here's all the stuff that's easy to write down, and here's all the stuff that, if I start here, I can get to the end of the proof. And there's usually one little gap you have to get across, right? This is that point in this proof. Saying that, hey, C is B times Y, but B is A times X, so C is actually A times X. That's B times Y. And now the rest of the proof, right, more or less writes itself. So C equals A times the quantity, X times Y, which is associativity. X times Y is an integer. Y is that. So up here I should have said these are contained in Z. Otherwise it's not really the definition of divisibility. So this follows from 3 and 4, which said X and Y were integers, and properties of integers. And so we've written C as A times an integer. That's the definition of A divides C. And there's your proof. Well, these aren't just random exercises. These are actually the foundational theorems for a sort of sub-branch of mathematics called modular arithmetic. And there's a number of versions of these theorems that we can do. For example, if A divides B, and A divides C, then A divides M times B plus N times C for any M N contained in integers. In other words, it's more than just A divides B times C. A also divides 3 times B plus 5 times C. A divides 17B minus 2C. So linear combinations of B and C are also multiples of A. This gets us into linear algebra if you're in 215. And a subset of that if A divides B, then A divides any multiple of B. Any B times N where N's an integer. And if we think in terms of divisibility, lots of things that we would like to have work a certain way will end up working that way. All right. So there's a thing here called the division algorithm. Which is actually not an algorithm, it's actually a theorem, but it's called the division algorithm. Oh, someone said the eigenvalue word. So there's a fairly long-worded mathematical way to describe the division algorithm. And I think by the time we get to the end of that, we've completely forgotten what course we're in and why we're here. So let me give you the gist of the division algorithm with some examples. And these are examples you've encountered already or can imagine. And I think this will give us the basic idea. So we're still working with integers. So A divided by B equals some quotient with some remainder R. So when we first learn about division in school, we don't get to fractions and decimals, we have remainders, right? So for example, 7 divided by 3 is 2 with a remainder of 1. 3 goes into this 2 times with one thing left over. Nine divided by 5 equals 1 with a remainder of 4. 5 goes into here once, almost twice, but not twice. It goes in once, and then you got 4 things left over. Okay, everybody all right with this? So we're going to be playing with dividing one number by another, getting some, whole number of times this goes in, and then some remainder. And all we're going to care about is the remainders. We're not actually going to pay attention to the quotient part. We're just going to worry about remainders. And that's going to be enough to do some really cool things. So if we make this a little more formal, when we say a divided by b is some quotient with a remainder r, what we're saying is, I don't want to draw a double arrow because I don't want to be logical. What we're saying is there exists some integer f such that b is equal to, well, I can make this easier. This thing right here is saying b equals a times q plus that remainder. Alright, so a divided by b is some quotient with some remainder. That's just saying that if we take a and we multiply by that quotient and we add that remainder part, we get back to b. Except I said it backwards. Alright, there we go. Alright, so 7 is 2 times 3 plus 1. 9 is 1 times 5 plus 4. A is b times q plus r. Got it? So 7 divided by 3 is 2 with 1 left over, which means 7 equals 3 times 2 plus 1. And if an elementary school teacher asks you, what's the remainder when you take 7 and divide it by 3, the correct answer is 1. Right? That gets you the gold star on your paper. But there are other answers that are possible. Because this is also true. Seven divided by 3 is also 1 with 4 left over. In other words, 7 equals 3 times 1 plus 4. So how many times does 3 go into 7? Well, it goes in exactly 1 time with 4 things left over. That's true. And if we're being really smart about it, this is also true. How many times does 3 go into 7? Well, it goes in 0 times with 7 left over. That's true. And this is just saying 7 equals 3 times 0 plus 7. But this is not as interesting as that, right? This is telling us that it's really close to a multiple of 3. It's actually just a little more than a multiple of 3. This is telling us, it's 4 more than a multiple of 3, which sounds like it's way off. But in fact, it's, just a little more than a multiple of 3. So this is more interesting than that. And this is way more interesting than that. This tells us nothing. Right? Anything divided by anything else is always, 0 with a remainder of that first thing. So this would be the answer you would want to put to get your gold star. And if you want to give your teacher a headache, you could do this. It goes in -1 times with 10 left over. Well, that's also true. And that's just saying 7 is 3 times -1 plus 10. Yeah, I'm sure that would get you far. Actually, it probably would. So we're interested in these remainders. And let me give you another way to give me a headache. Seven divided by 3, well, it goes in 3 times with -2 left over, which just says 7 equals 3 times 3 plus -2. So we'll throw that in our set of remainders also. And you can see that, like, if someone says, you know, what's the remainder when you take 7 and divide it by 3, you've got an infinite set of possible answers you could give. Some are positive, some are negative, some are close to 0, some are further away from 0. We're going to be interested in this one. This is, in some sense, the one that kind of tells us the most interesting thing, which is this is one more than a multiple of 3. And it's not that it's closest to 0, it's that it's closest to 0 without being negative. So here's the thing. There's always a unique remainder closest to 0, but not negative. And usually when we talk about dividing two numbers and asking for the remainder, that's the remainder we're interested in. The division algorithm is a theorem which basically says that there always is a remainder closest to 0 but not negative, and that it's unique. And proving that takes some work, and we're not going to bother proving it. Alright, so let's just look at the more confusing version of this. And, you know, if you like math, if you like symbology, this will actually be a clearer version of this. But in general, this can tend to obscure the intuition of what's going on. But, you know, this is the full definition of it. So, theorem. Division algorithm. So given A and D, given A contained in Z, and D contained in the set of positive numbers, there exists a unique quotient and remainder contained in Z such that A equals DQ plus R, and 0 is less than or equal to r is less than d. So what this is saying is you know, given a number and a divisor, where the divisor is positive, there's a unique way to write our number as some multiple of that divisor plus some remainder, where the remainder is between 0 and d minus 1. Bigger than or equal to 0 and less than the divisor itself. And so all of these, you know, write 7 as some multiple of the divisor 3 plus some remainder. But here we're looking for a remainder. Between 0 and 2. And there's only one of those. That's this case right here. Alright, so when we're using this in practical terms, right, 15 divided by 11 is 1 with a remainder of 4. 15 divided by 7 is 2 with a remainder of 1. It's these remainders that we care about. And this is just the good old modulus operator in C. If you go into a C program and you were to do 15% 11, you would get 4. If you went 15% 7, you would get 1. That's what the modulus operator does. It says, give me the remainder when I divide the first thing by the second thing. But the modulus operator is not trying to be wise. It's not going to come back and say, oh, it's minus 2, you know. It's always going to give us a number between 0 and the thing we're dividing by, minus 1. So the percent operator, the modulus operator, knows about the division algorithm. And it gives you that unique remainder which satisfies those properties. And it's kind of so obvious that we don't usually even think about it. Right? If we do a modulus operation, we kind of expect to get, you know, a non-negative number, and it's going to be smaller than the thing we're dividing by. And a lot of times in C we use the modulus operator just to simply answer the question, does A divide B? And we do that by just checking to see if B modulo A is congruent to 0. In other words, if the remainder when you take B and divide it by A is equal to 0. If B percent A, if B modulo A is 0, that means that B is equal to some quotient times A plus 0. In other words, B is an integer multiple of A. That's our definition of A divides B. So you've seen this before, you've used it in programming when you use modulus, right? But we're going to use this critically for the next week probably, to do a number of things relating to typically large integers. And here's, oh, we got a few minutes left. I don't have to give you a punchline yet. Well, here's the punchline. Here's why this is useful to us. What we're going to discover is that we can take, we can fix some moduli. All right, so let me give you a preview here. So a preview of coming attractions here. We're going to fix some divisor, which I'm going to call a moduli. So fix some divisor. For example, 7. So we're just going to think about dividing by 7, dividing by 7. Everything we do, we divide by 7. there's an infinite number of integers. And if I ask you to prove some theorem about all integers, you would have to, if you don't want to do an actual formal proof, you could prove this by showing that it's true for every integer. But that's going to be an infinite number of lines of your proof, right? You could show it's true for 0, 1, 2, 3, 4, -1, -2, -3. If you could do that for every possible integer, that would constitute a valid proof. But the problem is there's an infinite number of integers. But here's the thing, once we fix a divisor or a moduli, like 7, we can associate every integer with one of 7 numbers. We can make an association of any integer with some number between 0 and 6. And we're going to make that association by using the divisor algorithm. So we're going to take any integer, we're going to divide it by 7 and see what's left over. And so over here we're going to have the space of all integers, which is really big, but we're going to map that into a smaller space containing just 7 things. It's not a one-to-one mapping. We're going to have lots of things that map to the same number. Everything will be mapped to from something. And in fact, every number is going to have an infinite number of things mapping to it. But we're going to find out that once we've made this association, there are some things that if we prove over here, we will end up proving back here. And if I ask you to prove some theorem about the numbers 0 through 6, well, you can just see if that theorem is true for 0, 1, 2, 3, 4, 5, and 6, and if it is, you're done. But if we make this connection in the right way, we'll see that proving things over here will end up proving things back here. And the things we're going to prove are not just, academic theorems for the sake of proving theorems. They're going to be statements about how to do operations on numbers. And that's going to let us get to the following situation. We want to do something like take 2 really, really big numbers and multiply them together. And over here, those numbers might be 500 digits each. That's a lot of work. But if this number maps to a 4 and this number maps to a 2, we'll find that when we multiply them over here, the product, whatever it is, will map over to 2 times 4, which is 8. Which is actually the same as 1, because it's 1 more than a multiple of 7. So we'll be able to make statements about numbers and operations on numbers in this whole infinite space of integers by just working on this tiny little space with, in this case, 7 things in it. And 7 things, you can make a little 7 by 7 multiplication table and see exactly what you get when you multiply any 2 of these things together, or add them, or subtract them. And so working over here is going to be really, really simple. But if we make this association in the right way, things we do over here will tell us a lot about things that we could do over here. And so, for example, when we talk about cryptography, there's algorithms like RSA for doing very secure encryption that involves, multiplying huge numbers, taking some number with, 1,000 digits and raising it to, a power that itself has, hundreds of digits. And that's not possible to do over here. There's not enough time in our life to do those kinds of calculations. But we're going to move from there over to a space with a much smaller set of numbers, and we'll be able to do the calculations over here. And the answers we get over here will tell us something about the answers we would have gotten if we'd done them over here. That's the basic roadmap. Okay, that's why we care about modular arithmetic as computer scientists. Because a lot of these things we want to do involving really big numbers will make them doable by moving to this space of numbers modulo some fixed divisor. Alright, so that's a fair amount of hand waving or finger waving. But that's where we're going with all this. That's why we're interested in it. So what we have to do next is we have to develop this notion of modular arithmetic, which is working over here instead of working over in the set of all possibly really big integers. So we'll develop modular arithmetic, and it's really no harder than reading time on a clock. Clocks are basically a modulo 12 system. If you do military time, modulo 24. So we'll develop that system of modular arithmetic, and then we'll be off and doing all kinds of interesting things to do operations on large numbers. And we'll learn some cool tricks for like testing divisibility without having to actually divide. And then we're going to go on, we're going to talk about prime numbers, we'll talk about properties of primes, proofs about things related to primes, facts about primes, some really cool link-ins between prime numbers and the number e from your calculus courses, natural logarithm base. So we'll touch on that. We'll talk about the Chinese remainder theorem, and then we'll wrap up by talking about applications, which include validity checking of codes, things like barcodes, ISBN codes, and so on and so forth. Parity, hashing, which we're starting to talk about in 222. So applications to hash functions, and then we'll conclude with cryptography. And we'll look at a few examples of some simple ciphers, the problems with those, and how that led to the development of public key asymmetric ciphers. And we'll go through RSA in detail and see sort of how that works and how all the stuff that we're going to be developing over the next week comes together to the development and proof of RSA's correctness. So that'll be the next week. That'll be a number theory jamboree, and then we'll come back to proofs after that, and we'll start looking at mathematical induction. And that'll line up nicely with when we start talking about binary trees in CSE215. Alright, so that's the game plan, but for now we're going to call it a day and a week, so have a good weekend, and I will see you on Monday.